So over to you, Christina.
Thank you, Tavi. Kia ora koutou katoa. Haere mai ki toku kōrero. Hello, everybody. It's delightful to be here, and thanks to Tavi for the invitation to be part of this kind of global seminar series. I think it's an excellent idea. And when Tavi invited me, we were all in lockdown here in New Zealand, and it seemed like a good thing to do in the distant future. And now it's arrived, and we're back teaching live on campus thanks to our Prime Minister's team of 5 million. And I guess I'm saying that I'm looking forward to the day when we're a team of 7.6 billion. I don't think we're quite there yet. Ka tangi te tui, ka tangi te korimako, ka tangi ko aho. Nō reira, tēnā koutou, tēnā tātou katoa. What I want to talk about today is work that we've been doing here in Aotearoa, New Zealand, but with a number of international partners out on the RIS ice shelf. Starting in about 2000, I have no idea anymore, starting in 2015, we were funded by, kind of core funding, by the New Zealand Antarctic Research Institute to answer some questions about RIS ice shelf's vulnerability to climate change. And it's a big question. The view was that it was an interdisciplinary question, and so we set up kind of a program in which, really, in order to join the team, your question needed to be an interdisciplinary one, or the way we wanted to frame everything was that we had to work across disciplines to ask and answer questions. And so as a result of that, we have quite a huge team, and funding has come from all of our organizations, even from our regional council here in Otago. And we've drilled 2 boreholes, or 3 boreholes actually, in the RIS ice shelf as part of this work. You're looking at the camp on the central RIS ice shelf where we were in 2015 doing the site characterization, and then in 2017 for drilling. And I'll take you through that work and what we've learned so far. But since that time, the New Zealand government has funded what's called the Antarctic Science Platform, and now that kind of contribution is growing in importance to this kind of work. And the project that I'm talking about today has transitioned into kind of new science in new places under that program. So it's important to acknowledge that as well. There we go. It's also important to acknowledge that the tradition, the history of exploration in this part of the world is quite an old one. This is a quote from an article that was written in the Journal of the Polynesian Society in 1904 by Percy Smith. He was a surveyor, among other things. He was a speaker. He was British, but he was a speaker of Te Reo Maori, the Maori language, if an imperfect translator, but he wrote down many of the oral histories that were told to him. And in this case, he's writing about these great explorers of the Southern Ocean, of the Pacific as a whole, actually. In this case, he's talking about Te Aratanganuku, who was interested in following in the canoe track of his ancestor, Aotearoa. These folks were plying the southern seas a millennium or more ago, seeing the ice-covered ocean, ice-covered islands, tall cliffs of ice. These sorts of things are in those oral histories. And when you read how the history is spoken about, and when you listen to the karakia, the narratives of these great voyages, the way they describe things and the way they're talking about the work that they're doing is very similar to the way that the first European explorers of these places described what they were seeing as well. And I think that's it's important to recognize kind of the long history of work in this place, and our ancestors, our intellectual ancestors, our ancestors in the sense of exploration, and also our ancestors in just the sense of amazement and wonder and joy that these landscapes and these questions of how these places work bring to all of us. So I'm going to talk about sort of our, not adventures so much, but our work in the central part of the Ross Ice Shelf. This is a drone image that was captured by a New Zealand Geographic photographer, Neil Silverwood, as we were heading out for the 2017 season, and these folks are driving along the South Pole Traverse Route that the U.S. National Science Foundation maintains and navigates every year. So it's important to recognize sort of that contribution and connection as well. So the big question: when, why, and how rapidly is change going to arrive in this part of West Antarctica? So I'm showing you here just a map that we're probably all familiar with. This is the surface elevation all around Antarctica and the sea floor bathymetry underneath it. Apologize, I realize I've left the color bar off of the bathymetry. That's all right, you can probably figure it out. There's a continental shelf and then it gets deep. Those two tents that you see there, use my little hand to point at them, the two tents on the Ross Ice Shelf here show you the places where we've been working. I'm going to talk about this central Ross Ice Shelf site today. We know from the geologic record, the Andrel record over here near Ross Island, that past warm climates have been characterized by a lot less ice in West Antarctica. And we expect on some kind of time scale, and we know from observations on the Amundsen Sea coast, right, that marine interaction with low elevation ice, with floating ice shelves, is an important way that change arrives to West Antarctica. And the case that we made in this project was that what these questions mean, we really need to understand are rates and thresholds. And rates and thresholds are generally processes interacting together. So that kind of gives the motivation for the interdisciplinary approach. On this map, now just the bathymetry, and there's your color bar. I'm showing you all the places where boreholes have been drilled through ice in this part of West Antarctica. So our two sites, we've called them perversely HWD2, Hot Water Drilling Site 2. That's the place where we, actually, there's also a Hot Water Drilling Site 3, which was the first one that we drilled. That was our kind of testing site for a lot of equipment near Scott Base. But Hot Water Drilling Site 2, the one that we were working at a couple of years ago, HWD1, site where we were last season at the Cam Ice Stream grounding line. Then Coleman High, a site quite near the front of the Ross Ice Shelf. There have been some really nice papers written about oceanography at that site, and that kind of warm surface, summer warmed surface water getting in underneath the ice shelf front at that location. Of course, the famous, Doug is here, J9 from the 1970s, and then the Wizard site further south. So our boreholes kind of fit in this context, and part of our motivation for picking this central Ross Ice Shelf site was that we could think in some way of having some sort of transect-like feature out there among these different sites. We wanted to be far enough east that the seafloor sedimentary record would look as much like a West Antarctic record as it could, but not so much in the middle of whatever gyre is under there that the oceanography would be really boring. Also, we had to be able to get there. This site is right along the road. So we didn't exactly throw a dart at a map, and those were the constraints that we worked with. So zooming in, another map of the bathymetry, but now with a color bar that brings out a lot more detail. This is the BedMap 2 bathymetry. The broad features are ones that would hold up with the Rosetta bathymetry, right? We have a deeper sector of an ice shelf cavity over here where we were, and we're actually kind of close to the boundary between that deeper part of the cavity and a shallower reach of the cavity over to the east. So this site, the ice is relatively thin, about 360 meters, and the water column is another 100 or so meters beyond that. So deep water, shallower ice at this site. And if you look at the features on the seabed, there's broadly a trough and a little bit of a saddle in that trough, and our aim was to be on the west Antarctic side of that saddle. Okay, if we think about the ice, where the ice came from that's overhead, you know, the ice shelf is a composite of ices of different origin. There's terrestrial ice from glaciers and ice streams. There's new meteoric ice, snow falling on the surface, and then possibly accretion of marine ice onto the bottom. At our site, once we made the hole, then we knew where we were, and we traced the flow bands back upstream. This is a map showing you surface elevation, so we with pretty high resolution, so we can see all of the flow traces in the ice shelf quite easily. If you trace this flow band back upstream, you end up in the Liv Glacier, which is a moderate glacier flowing through the Transantarctic Mountains. Okay. So that's, I think, the big context that we need to think about this site. As I've said, our view to try to understand how change arrives to the ice shelf is to be interdisciplinary and say that oceanographers and glaciologists need to learn to think at least a little bit like each other. Folks who are studying the seabed sediments need to be thinking like a glaciologist to understand what that record is about, and vice versa, and all the possible combinations. So on this kind of cartoony slide, I'm just showing you the myriad things that could be going on that we want to think about, right? So we've got an ice shelf that is the floating extension of the grounded ice sheet. That transition right here, the grounding line, the transition between the grounded ice sheet and the floating ice shelf, is the place where the water that's being stored on land in the ice sheet returns to the ocean. So we care to know where that boundary is. We care to know if that boundary is changing location. We care to know all of the forces, the stress budget in the system that gives us the placement of the grounding line. And we want to know about the boundary processes that can cause those stresses or those forces to change, or cause just the thickness of the ice to change. So for this study, or this project, we're interested in understanding seafloor sediments, both for the paleo record and for their properties that can influence flow near the grounding line. We're interested in ocean circulation in the cavity, either bringing energy into the system, driving mixing, redistributing ice on the underside of the ice shelf, being a source for crystals that can grow sea ice out at the seaward edge of the ice shelf. All of these things are of interest. Probably said enough about that. So the place where we've gone, this central ice shelf site, we aim to think about the ice itself. We aim to learn something about the ocean circulation, make sort of direct observation of ocean circulation in the cavity, ocean water properties in the cavity, and to collect sediments from the seafloor. So what I'm going to tell you about in this presentation, realized I've lost there's my clock. One, that basal ice, that accreted ice on the underside of an ice shelf that we think about as being marine might not be what you think it is. There's been persistent ice shelf cover at this site since grounding line retreat. And the sediments are, everything in the sediments, the carbon in the sediments is pretty old. And then finally in the oceanography, there's very fine scale thermohaline interleaving that is going to be associated with how mixing actually happens in the interior of the cavity itself, away from the boundaries. Okay, this is another drone-based photograph taken by Neil Silverwood. It's showing our camp layout at this site. I actually drilled 2 boreholes, and I'm showing you the farther away borehole, but we'll look at that as we go along. But you can see kind of all the features of one of these camps. And I guess what I really want to draw attention to is that big, beautiful orange drilling tent that you can see up here, which I've decided is the civilized way to do this kind of work. This is the basic structure of the hot water drilling system. It was built at Victoria University in Wellington following a British Antarctic Survey design that, as Alex Pine and Darcy Mandano, the geologist and engineer who really run this show and are the great innovators, it's been Kiwified. But you can see here, this was at this site we drilled 2 boreholes. One to leave and to install an ice anchored mooring hanging into the ocean cavity right at the start of our season. And then we moved 500 meters upstream to make a second borehole where we did a lot of work during the season. But just you can see the system of burners here in this temporary setup, the generator setup. Here's our mast, and then that flubber with the seed water on the surface. And the expensive kilometer-long hose with a lovely cover over it in that image. Here's our beautiful tent where we have been working both in 2017 and then this past season at the CAM ice stream grounding line site. There's a view inside the tent, so you can see the drillers are reaming the borehole at this time. There it is in the front of you. You can see the drill hose there coming down. This is the second entry for the subsurface well and the pump that goes down into the well. It's a very nice place to work with this kind of weird orange glow. As I understand it, the tent was meant to be white in the middle and orange on the ends. There you go. All right, and there's another view, and I'm showing you this view for 2 reasons. The maximum diameter for the borehole is about 30 centimeters, and also to show you how beautiful and clean the snow is at the start of the season. All right, once the borehole is drilled, the first thing that we do, our NIWA colleagues from Wellington make the first kind of oceanographic observations and send a camera system down to have a look at the borehole, see what we've done. So we're just going to work our way down through the ice column here. They have a better camera now and much more brilliant images, but these are the images from 2017. Right, so if I go back, we're up here. You can see this is the cable and the hose for the pump that's down there in the subsurface well. So we're still up in the fern. You see all that corrugation from the jets on the reaming tool. And as we go down deeper into the ice shelf, we've got this nice bubbly glacier ice that we're moving through. And then down at the bottom, this completely blew our minds. In retrospect, it completely blew our minds. The bottom 60 meters of ice at both of the boreholes looks like this. So this ice is 360 meters. It's not that thick. It's just your average typical valley glacier. This ice is bubble poor, and it's shot through with sediment of many different grain sizes. We were not expecting to see that, and I'll talk a little bit more about that in the next few slides. We come right down to the very bottom of the borehole. So this is an kind of oblique image we're looking out, so the bottom of the borehole is up here at the top, and we're just looking out right along the base of the ice shelf. So you can see right along the base, it's a nice, sharp, clean base with just a few crystals, a few centimeters of very fresh looking platelet ice kind of growing on the base of the ice shelf. And you can also see that sediment in the ice up above. And here's another view, just a little bit deeper, looking out across as far as the camera can see, that several centimeters, just a few centimeters of very fresh and beautiful looking platelet ice on the base of the ice shelf at this site. This used to be a movie, but it doesn't work anymore because that's the way Flash is, I guess, but that's all right. On the right of the slide, we've got two more images of really focusing in on that transition zone from the overlying bubbly glacier ice to that bubble pore, sediment rich would be a stretch, but sedimenty deep ice. And the point that I want to make is that the contact is very sharp, and in this borehole it's steep. So in both of these slides, or both of these images, we're looking down into the borehole. So the one on the top is a little bit higher, it's just above the transition, and the lower image here, we're sort of right at that transition at about 307 meters. So if you're looking down the borehole, behind you there's bubbly glacier ice, and in front of you there's this bubble pore stuff. It's a very sharp transition, and you can see here what certainly looks like an ice-filled fracture extending from that boundary. So I've drawn sort of a cartoon on the left-hand side of the slide of what that looks like in our minds. And then in the middle here, this is the reaming tool that has come up from that deep ice, covered with sediment from that deep ice. And you can see that there are many different sizes of grains in that material. Okay. So we'll talk a little bit more about what that stuff is, but here's then kind of the schematic. That sediment is all terrestrial in origin. It's, for our group, beacon group kind of stuff. We found no diatoms in it at all. There's no sense of any marine contribution in the sediments that we recovered from that deep ice. The basal boundary, that thin layer of platelet ice, I'll provide more support for this interpretation when we look at the oceanography. But we say that acreted ice got there from the glacier from which this flow band came. I'll talk a little bit more about that in a minute. Then that basal layer, that thin layer of newly accreted ice, looks very fresh. We think it's ephemeral. Perhaps there's a cycle of melting and freezing going on the underside of the ice shelf. When we look down at the sea floor, so the bottom image on the right here, what we see is drop stones, right? With this kind of thin cover of very fine clay. It's very, very fine. All the geologists in camp tested that the way a geologist would, and it's slightly salty and very fine. So there are drop stones, which we often associate with icebergs floating around and melting out. That's happening right here. But the seabed is not plated with them. It's infrequent. So we put that together with the view of the base of the ice shelf together with what we will learn later about the oceanography, and that leads to this view that melting and freezing here is an ephemeral thing. Okay. All right. So what more about that deep basal ice? We have imaged the whole region, using low frequency radar system that is on sort of a long-term loan from Ginny Catania. This is Martin Forbes, who's been running this. He's a postgraduate student here at Otago, who's along with Kelly Gregg and Greg Leonard, have been running this system with my feeble help. I like to say it's a really long wire, and they say there are resistors in there too. So what do we see with the radar imaging? This is just one, we've got a number of these, obviously. This is just one section going across that Liv Glacier flow band. The Liv Glacier flow band here, this gray bar at the bottom is showing you where that is. These various colored lines are just flow traces that we trace back upstream to figure out what kind of ice we're looking at. They continue on to the radargram up above. Here is where our two boreholes were drilled, the one for the mooring and then the one for the main season operations. This blue line on the radargram is the base of the ice that you would predict if you were using flotation. So this is all full of ice. This is that ice that we drilled through. But the brightest reflector that we get is up above it, right? So that's kind of a classic signature for something that folks interpret as marine acreted ice, but it's not, right? We have direct observational evidence that it came from here. This is the Liv Glacier, and the interpretation then that we make is that confluence, so the grounding line is sort of right out here along the coast. This confluent zone where we have glaciers coming together and flowing through sort of a narrows in the coastal margin. There's heavy crevassing at the surface and the bottom. Basal meltwater is rising up, taking some sediment with it and freezing in to those basal crevasses. It then gets entrained in the flow band and moves slowly for hundreds and hundreds of years out to the site where we've drilled through it. So out of that, we conclude that we've got to think some more about what basal accreted ice actually is when we image it using radar. All right, so moving on to then more with the sediment. We want to connect with the sea floor. Here's Gavin Dunbar from Victoria University getting gravity core ready to go. This is an AVI gravity core. It's exactly what it sounds like it is. We lower it down to right above the seabed, release the brake on the winch and let it fall into the seabed and penetrate as far as it can. And this is what I want to point out. Look how much of a mess geologists make of your beautiful snowy environment there. That's all right, because they also do this. This is one of the cores that was collected. In fact, we collected quite a number of cores at the site because the ice was moving, right? So we've got many opportunities to collect material from the seabed. All of them are about 65 centimeters long. So there you can see there's a cap on the base of the core barrel, and you can see that kind of sediment, and then the pretty clear ocean water on the top of the core barrel. There's the seabed, pretty exciting. You can see some bioturbation perhaps, and you can see some of those drop stones at the surface. Okay. On the lower part of this picture is that very soft, most of the sediment column is very fine clay. We'll look at some CT scans in the next few slides. And then at the very base, this is the stuff that we never managed to penetrate our way through. That's a coarser grained, more compacted basal till, all right, sort of a diamict that represents when the ice was grounded at this site. Okay, and then this stuff up above it is the sediment deposition since the grounding line moved past this site. Okay. So here's one of the cores split in the context of the site overall. So down at the bottom, I've got that consolidated diamect. We've looked, Adam Martin at GNS Science has done quite a detailed analysis of the pebbles and sand fraction. And what we see is that those are central transantarctic mountain rocks. It's the same stuff that's in that accreted ice. Oops, oh my gosh, that was exciting. That was the Mighty Mouse helping me out there. And the accreted ice overhead. Most of the core is very soft, very fine, generally fine-grained material with occasional drop stones. It's all old reworked material, diatom fragments from the late Miocene and early Pliocene, along with some kind of pelletized, the same stuff, but in a pelletized form. And when we get up to the very top, the very recent most part of the sediment, there are a few forams, there's some turbation, no modern diatoms at all. Okay, so now I'm showing you CT scans through one of the cores. So these are just different slices through the same core next to the split core, and the lighter color is denser material, the darker color is less dense material. We see at the base that consolidated material very clearly. We see those larger clasts. As we go up the core, we see kind of more uniform texture, not too many drop stones, a few. We see these till pellets. See if I can do this without moving my slides. There's a nice till pellet right there. You see these, they're a little bit squished and elongated. When you take them out of the core, they're very, very soft, very fragile. They smear right away. I also see these two layers that look different, that look disrupted relative to the rest of the post-grounding line sediment that we see at the site. Okay. If we look at the fabric of the material using magnetic susceptibility or anisotropy of the magnetic susceptibility, I'm showing you here in the middle foliation, so a proxy for bedding, and on the right-hand side lineation, a proxy for current strength. We see, focusing on the foliation, we see that there are transitions in the strength of the foliation at those disrupted layers. So below a disrupted layer, the bedding is stronger, and above it, it's weaker, and that's the case in both of those. We also see in the lineation kind of peaks right before those layers. So slightly stronger benthic current happening right before those disrupted layers are formed. All right, so just in the context of kind of grounding line retreat from the continental shelf edge, the map on the right here, I'm showing you a few of the records of some dated, some not. The pink lines are kind of grounding line, stepping back, interpreted mainly from morphology from the continental shelf. And the point I just want to make is that it's an episodic thing, and the rate at which it goes and the pattern in which it goes depends on shoals on the seafloor, right? It's quite spatially variable, and that provides us some context to think about the record that the sediments are giving us. And basically what we see are three different conditions. We see the ice is grounded at this site. We see that we're grounding line proximal, so most of that sediment, so the diamect at the bottom, grounded at this site. Most of the record is grounding line proximal. All right, so the grounding line is right there nearby. And we interpret those consolidation events to be regrounding. So the grounding line is nearby, ice regrounds, goes afloat again, regrounds, goes afloat again, and then it's gone. All right, and then we're just in that null zone. So grounded, grounding line is sort of messing around at the site, and then it's just gone. Unfortunately, all of the carbon in our cores is old. So we cannot date that sequence. We don't know how long it took for that to happen. But these delicate features are very well preserved. All right, so third thing I want to talk about in my remaining time here, this is Craig Stevens pointing in the direction of the ocean. He was the lead oceanographer for our work, and I'm just going to talk a little bit about what we're learning about the oceanography in the ice shelf cavity. So here's a kind of cartoon view of what we generally expect to see. We have we would expect high salinity shelf water to be circulating, to making a benthic, sort of the seabed boundary layer coming into the cavity. We may or may not see circumpolar deep water accessing the cavity, at least somewhere near the front. How far in it penetrates, good question. We would expect meltwater coming from deep within the cavity, rising up along the base, and then some potentially interior layer, that deep ice shelf water, that's some kind of mixture of these waters from different sources. So what did we actually see? Again, this is the place where we drilled, and what we know of the basal ice up to that point. Here are from the season, so we have additional data now from the mooring, and Craig, we're working on understanding that data now. These are data from 2017 from repeated high-resolution casts from the base of the ice shelf. So up at the top of these plots, we have the base of the ice shelf, and I'm showing you pressure, but it's about the same as depth. In the middle of the slide here, the salinity, and on the right, potential temperature, so the pressure adjusted temperature, and then on the left there, an interpretation of kind of where these layers are. So down at the bottom, indeed, we've got a high salinity benthic boundary layer that varies in thickness over the time of our observations, between about 20 and 40 meters. We've got an ice shelf boundary layer up at the top that's cold and relatively fresh. So you can see that nice fresh. So that's meltwater, cold meltwater. I'm showing you the freezing point, the depth dependent, pressure dependent freezing point there as well. And then an interior, a cavity interior that is quite stratified. The whole thing is quite stratified with kind of two different parts. The deep part is very stable, so this kind of area B here, and then an upper section that's highly variable. And what you're seeing here are the different colors are different days or different times of day, different individual casts down through the full water column. Here I'm showing you a TS diagram of that same data, so you can get a sense of sort of where those different water masses sit in terms of what water mass they are, or where, I guess, what water masses have mixed together to make them. We're pretty far on an extreme part of a TS diagram, I have to say. The other thing you can see is that ice shelf basal layer is sort of right along a melting line or a freezing line. So that's kind of supports that initial interpretation that melting and freezing on the base of the ice shelf are probably transient features of that part of the system. Okay. And then the kind of final thing to think about is what's going on in that layer that I've called C here, kind of the upper part of the cavity interior. And if we think about, this is the cartoony kind of interpretation, that thermohaline interleaving, which can drive some diffusive convection, some mixing, or is driving, mixing in that upper part of the water column. That's a tidally generated feature. So if we imagine that we've got meltwater coming from deep features on the base of the ice shelf, in our location, that's the keel of Liv Glacier, potentially the keels of other major transantarctic glaciers that are flowing out and joining the ice shelf. Melting that's happening, that really cold fresh water that's being produced as it rises up and peels off, kind of finds its neutrally buoyant correct depth and circulates into the cavity as the tide causes the whole system to adjust. We're going to get this interleaving of slight variations in the temperature of the water, and then that's going to drive mixing in that part of the water column. So this is pretty amazing. Craig Stevens was exactly the right oceanographer to be looking at this. He thinks a lot about these sorts of very high resolution features and makes sense of them. You get a sense of the importance of the tide to the whole system, and you certainly get a sense that many different scales are going to matter if we want to correctly simulate in a model circulation of the ocean in the cavity underneath the ice shelf. And as you may know, you can read all about it in a paper that was just published a few weeks ago in PNAS. All right, so if we put all of this stuff together into kind of one big story, there's still a lot more writing that we're doing. There's a lot more story to be told, but certainly persistent ice shelf since grounding line retreat, it certainly looks like it was rapid. We should be careful about what rapid means, though. There clearly are these regrounding events, also of unknown duration. We have, though, since that time, clearly had these sort of null zone conditions, right? The facies with the till pellets are very clearly grounding line proximal, and then it's just gone, and we have very low sedimentation rate, and we have these drop stones coming out of the underside of the ice shelf. Okay. The ocean cavity conditions are generally as we expected, but with these interesting fine scale details that are going to matter for understanding how mixing happens in the cavity and how in the cavity as a whole ice shelf basal melting and freezing is regulated. Okay, so this is my last slide, just to acknowledge the huge team of folks that it took to do all this. There are other parts of the science that I haven't talked about at all. Those are some happy microbiologists up there in the upper right. Amazingly dedicated folks who got stuck out there with us for quite a long time. Every night they got up in the middle of the night and recollected their live water samples just in case an airplane came. It never did. They drove back to Scott Base instead and still got there just in the nick of time. It's pretty remarkable. Support from Antarctica, New Zealand, of course, as well, and from, I should say as well, and contribution from Georgia Tech, Brittany Schmidt, and the IceFin team, who were supposed to be at this site, along with another couple of microbiologists, but the same weather conditions that prevented Fede and Sergio from getting out, prevented them from getting in, which was a huge disappointment. But they were there at the Cam ice stream grounding line this season, and we're grateful for that. So I will end it there, and I'm happy to look at that. I've got time for questions. I did well.
Fantastic, you did extremely well, and I have to say I'm enormously jealous of your tent that you drilled in, and looking at how neat and tidy all your camp was. We had so much snow at our Beamish site. So questions for Christina. Let's
I can stop. I have to go to the Should I stop sharing my slides, or maybe we'll go back to a slide?
What I will do actually is I'll just share the slide which advertises next week's seminar.
There it is.
Oh. I think we've got it there. So, if anyone has questions for Christina, can you put them on the chat? I'm going to have to stop sharing that slide because I can't see the chat anymore.
Oh, yeah, here we go.
Questions for Christina? If you just type onto the chat to say that you've got a question, then we can unmute you. Doug, do you want to unmute yourself, Doug?
Yes, Christina, fantastic talk. Now, did you see any animals that are bigger than the microbio that Fabio was urging for? Fish or anything like that?
A few. If you want to annoy an oceanographer, that's the first question you ask them, right? I learned that the hard way. Yeah, actually, we saw some kind of brittle star thing down there. We saw, I'll say this incorrectly, a chaetonath. What else did we see? We saw something that looked like a fish that was hanging out on a small one on the seabed and then swam away. Yeah, oh, and a krill. We saw a very pink krill. It's got to be like having the worst year of its life, but it's not going anywhere good.
So, any other questions?
You're just going to ask about fish? Aren't you going to ask me about that amazing not marine ice?
Tell us more about the amazing non-marine ice.
Thank you, Doug. Yeah, so the first thing is, so we were using phase-sensitive radar, right, to try to characterize melting and freezing all around the area and then along the whole road to the site. And the return from the base was very diffuse, and we thought, oh, it must be mushy down there. And so it was a real surprise to see there was a nice sharp boundary and that there was something else down there. And that kind of inspired us to just think about like suture zones, different flow bands in general, and we've now sort of profiled across quite a number of flow bands in the central part of the ice shelf to look at relationship between internal layers in flow bands and in margins and the deep ice. And there are other places that look just like this, where there is deep ice that's accreted onto the bottom that's clearly not coming from like a suture zone where you might think marine ice would be made. So some of that accreted ice out there on the bottom of the ice shelf is terrestrial. And I think that's important for how we think about how the heterogeneity of the material is affecting fracture propagation, temperature, that kind of thing. Also, drop stones without disintegration of the ice shelf. Very cool.
Do you want to ask your follow-up question, Doug, and then I'll...
Sorry I'm hogging the questioning. I'm just enjoying this incredible science so much. In the past, particularly...
Thank you for our advisor, Doug.
In the 70s, there were lots of these stripes that were basally painted along flow, and they were interpreted as marine accretion ice. How much of that now do you think could actually be terrestrial ice, thereby reducing the inventory of marine accreted ice?
I think some of it. I think the message is you have to look upstream and be very careful in thinking about exactly where that ice came from. Yeah, so like, so you have to understand the process rather than just use your intuition.
So Imogen, we have a question from Imogen Brown. You're unmuted.
Hi. I had a question about those layers that were interpreted as potential regrounding. And so what do you think may have caused the change in bottom water or bottom current speed prior to those readvances?
We think it's just the water column getting thinner.
Oh, okay. Interesting.
Yeah.
All right.
You know, that's just the hydrodynamics, right? If as the column gets thinner, it's got to spin a little, it's got to move a little faster.
Okay.
The big question is, why does that happen? And chances are it's just because the thickness of the ice shelf is not constant over time, right? If we've got flow variability upstream and we've got a little bit of grounding happening somewhere, that can cause sort of transient waves of thickness changes, and that can cause sort of transient grounding and ungrounding as well. We certainly see evidence of that today, like around Prairie Ice Rise, so it's probably something like that.
Great, thanks.
Paco.
Yeah, it was a typical drilling speed. Oh, I don't remember. I completely don't remember. I don't want to say something wrong. It's pretty fast. Yeah, I'll just say something wrong, Paco, but it's, you know, it's, by the time they start the pilot hole, it's, you know, it's about 24 hours while they're getting everything sorted and working before we have a complete pilot hole that they then start reaming. The first time they drilled through that deep ice, they, this is still being recorded? Yeah, okay, so the lance got stuck. The first time that they drilled through, in the first borehole when they drilled through that ice, and the interpretation, as I understood it, was that there was a change in speed that they hadn't anticipated, or there needed to be a change in speed that they hadn't anticipated, and they were trying to go too fast through that deeper ice, and that caused the problem. And then once they'd accounted for that, things went fine again.
Okay, thank you. It was really nice talk.
Thank you, Paco.
So we have a question on the chat here, really good question actually. It says, can you comment on how spatially widespread the debris is? And do you think what you called is a local feature, or would you expect to find it everywhere upflow if you drilled lots more holes? That's a question.
Yes, we think we would find it everywhere. I could go back to if you remember, can I share my screen again? Oh.
Sure, yes, go for it.
Excellent. All right, let's see. Isn't it good that I cleaned up my desktop so nobody can see other crazy stuff here? Let's see. So if you just look at this one radargram and you think about kind of the boundary between either ocean or some other ice as it rises up in this sort of lozenge shape, right? That's the whole flow band, and here's the margin, right? So it's thicker in the middle. All of our crossings of this flow band look like this. So we obviously didn't drive through the camp, but when we go further upstream, we see the same thing. I don't have a quick image to show you of this, but when we drive along flow, it's just a very chaotic set of reflectors down there of hyperbolae, and we interpret that to be that we're driving across basal crevasses that are giving us all kinds of reflection, off-nadir reflections, right? And it's just a big jumbled zone. So we think that it's this basal crevassed flow band that extends as far as we can image it And all of it is full of this refrozen basal meltwater. And we would expect it. There's no reason to think it's different. I mean, we've only looked at it at those two boreholes. We saw exactly the same thing in both boreholes. There's no reason to think it would be different unless the sediment supply ran out, I guess. And as Doug pointed out, indeed, if you look at the airborne radar, right, you see that accreted stuff going all the way back upstream. This ice spends a long time right along the coast, right? So it comes out of Liv Glacier and it turns left and it spends a while along the coast before it turns out, because ice from Mercer ice stream is in the way, until it can turn out into the main flow. And we thought for a long time, could that stuff, you know, be anchor ice? Could there be some like ephemeral regrounding right along the coast? But it's hard to make that work with the fact that there's no marine stuff in it, and with the fact that the boundary is so sharp, and just it's sharp, and it appears to have fractures coming off of it. It just looks like crevasses. You put that together with the radar imaging, and it's hard to think of it as being anything other than like a dense basal crevasse field that's been filled with refrozen water.
Thank you very much, and thank you for that question. It was a great one. Any final questions for Christina? I'm guessing that we've run out of questions, but thank you so much for the seminar, and very exciting to be sitting here in Europe, in COVID-filled Europe, talking to, or having a talk from somebody in New Zealand where you've solved all of the problems. I should probably just remind people about next week's seminar, which is going to be presented by the 2 Graham Cogley Award winners for this year. So we have Paul Waver and Carlo Luciuli presenting next week. So hope to see you all next week. Thank you very much, Christina, for a fantastic talk. Yeah, thank you, Doug. Yes, indeed. And see you all next week. So thank you very much, and see you soon.
Thank you all. I just want to point out to Magnus before you go away, you should see my library back there. That's the complete history of the journal right there. Oh, and the annals are down below. All right. Bye, everybody. Thank you so much.
Bye, and thank you.